Hello and welcome back to MetaMath. In this video, I'm going to be covering the 2019 AMC8 problem number 24 as part of the AMC8 Final 5 series. So the problem reads, in triangle ABC, point D divides side AC so that the ratio of side AD to DC is 1 to 2. Let E be the midpoint of side BD and let F be the point of intersection of line BC and line AE. Given that the area of triangle ABC is 360, what is the area of triangle EBF? So what I'm going to do with the diagram that they've given us is just enlarge it a little bit so we can work more clearly with what we're given. And now the two ideas behind this problem is the concept of simple mass points and area ratios. So to give a quick overview of simple mass points, we really want to think about it as a seesaw. So we can envision it like this. So the idea of a seesaw is because since the ratios of the sides themselves are not the same, so this side is obviously much smaller than this side right here. So to compensate for that, we want to place a quote-unquote weight right here, which is much greater than the weight right here. Now, to see how this might work, if we have a ratio, which we do, we have plenty of ratios in the triangle. We have ADC is in a ratio of 1 to 2. So the problem we're dealing with is this line right here. If we thought about it as a seesaw, D would be the balancing point of our seesaw right now. So the ratio is 1 to 2, but the weights have to be placed in reverse. So because they're in a ratio of 1 to 2, the weights have to be in a ratio of 2 to 1 to really balance it out and kind of act as a balance on D. So the product on this side has to equal the product on that side, and 2 is equal to 2. So the total weight on this system is the sum of the weights on A and C, so the total weight is 3. Now this idea of mass points is especially useful when it comes to finding area ratios. So in a triangle, and this is an arbitrary triangle, so we can go ahead and draw it so that we have a base 1 right here and a base 2 right here. And the side lengths don't really matter for this purpose, but what's important is that the fact that they share the same height. So both triangles have a ratio of their areas as the ratio of their bases. And if we were to think about this, we can call this A1 and this A2. A1, the ratio of A1 to A2 is the ratio of their areas, but the ratio of their areas is simply base 1 times height 1 over 2 divided by base 2 times height 1 over 2. Now, if you go ahead and simplify this, the heights will cancel out and the 2 will cancel out. And the ratio of the areas is nothing but their bases, the ratio of their bases. So this idea that we can find the ratio of two areas as the ratio of the bases is especially useful with mass points because we've already found the area of the ratios by using weights. So we can go ahead and apply that to this problem right here. So we know that the ratio of, AD to DC is 1 to 2. The weights are then 2 to 1. Total weight is 3 at D. We can also use the fact that E is the midpoint of BD for this problem. So B has to have the same weight as D, and E must have a total weight of 6 because it's the sum of weights B and D. That means that the total weight, or the ratio, must be 1 to 1 because the weights on either end are the same. Now we can find the weight for F because we know that the weight on A is 2 and the weight on E right here is 6, so the weight on F must be 4. Now the ratio of the sides is in reverse of the weights, so the ratio is actually 4 to 2. And lastly, we have the side BC. We actually have the weights 3 to 1, so we know that the sides are in ratio 1 to 3. Now we can go ahead and apply this idea of area ratios. So if we were trying to find the area of triangle ADB, and when we represent area ratios, we generally use brackets around the triangle. So the ratio of ADB to BFC, which is our triangle right here, they're in a ratio of 1 to 2. And we know that these two triangles form the entire triangle, which has an area of 360. So these have to sum to 360 themselves. So we know that the area of triangle ADB is 120. So BFC has an area of 240. Now, what we can do is we can go ahead, and I'm going to use a different color here, red, to break the triangle we're trying to find, which is EFB, into areas we know how to find. So since we know how to find ADB, we can also go ahead and find this area right here, because we can also find the area of this smaller segment right here and then subtract it out. Subtract this smaller segment out of the triangle ABF to give us the area we really want, which is this right here. So we did the side ratios already, and we can go ahead and find the ratio of the smaller subsegment first. So the ratio of BE to BD is the ratio of triangle ABE to triangle AED. So BE to ED, that's in a ratio of 1 to 1. So their areas are actually congruent. So that implies that this area right here is 60 and this is also 60. So the two areas of those smaller triangles form this larger triangle right here, they're equal and they're both 60. Now what we can do is we can find the area of triangle ABF, which is going to be triangle ABF. And while it is 1, it's in a ratio of 1 to 3 with BF to FC, but it's also in a ratio of 1 to 4 with the entire side length. So what we can do is we can say it's in a ratio of 1 to 4 with this entire segment BC rather than comparing it to FC. So ABF over ABC, the ratio of those two areas, is 1 to 4. And that's exactly the reason why we compared it to BC rather than FC, is because ABC is an entire triangle. So that means the ratio must be 90 to 360. So what we've determined from this is that the area of triangle ABE is 60, and that the area of triangle ABF is 90 because it's 1/4 of the entire triangle, or you could view it as it's in a ratio of 1 to 3 with this slightly larger triangle that forms the entire triangle. So with this information, we can go ahead and subtract the two triangles to give us the area that we were searching for, this red area, which is triangle EBF. So triangle ABE triangle ABF, which is a larger triangle obviously, minus triangle ABE. The difference of those two triangles gives us our area that we want, which is EBF. So the area of EBF is 90 minus 60, which is simply 30. So the answer to this problem is 30. Now, the main takeaway from this problem is the idea of simple mass points. So the idea of simple mass points is especially useful because we can apply it to any type of problem that involves simple CVNs and lines. So any problem dealing with a triangle that only has CVNs, which are again lines that start at the endpoint of a triangle's vertices and have another endpoint on the triangle. So this right here would be a CVN. B, we could call it BD right here. But for example, this right here, EF, would not be a CVN. So we wouldn't be able to apply mass points with EF. If we were to remove it, however, we could apply mass points. So mass points is especially useful when we're dealing with area ratios in triangles like this. If you guys have any questions or problems you would like me to cover, or even topics that you'd like me to cover, please leave a comment down below, and feel free to subscribe and like if this video helped you. Thanks for watching and stay safe.